Hello, and welcome to episode 7 of the Minimapper series. Today we're going to be talking about choosing a photoencoder. We talked last time about the mechanical constraints on this thing, and they turn out to be much more important than anything electrical to do with these things. So we'll go through the kind of spreadsheet and process of elimination mechanism to choose one of these things. First, though, let's say a few things about what a photointerrupter actually is. It's very simple. It's basically an infrared LED plus some kind of detector with a gap in between the two that you can interpose some object to block the radiation from the LED to the detector. And so you can detect when there's a thing in the way and when there isn't. These things come in two flavors, transmissive or reflective. We're going to be using a transmissive one, and it has this slot here to put some object into, interpose in the optical beam, which goes across here. You also get these reflective kinds of these things, where you shoot radiation from the infrared LED and it bounces off of an object and you detect that. So you can detect the presence of objects that way. We're not going to be doing that. We're going to be using a transmissive photointerrupter. Another distinction that's quite important is that these come in two further varieties, either a phototransistor kind, where you just have an infrared LED and a phototransistor in one package, so you have four leads, anode and cathode for the LED, and collector and emitter for the phototransistor. And so the output you get here is an analog output as a current from the phototransistor, and you have to process it yourself in whatever way you do. The other kind of device, this one on the right, is what most manufacturers call a photo IC device. And again, this has an LED, so you have a lead for the anode and a lead for the cathode. But then on the output side, you have a power supply, positive and negative, and you have an output here that's a logic level output. So what you have here, you have a detector. In this case, it's shown as a photodiode. There's an amplifier, in this case a transimpedance amplifier to turn the current from the photodiode into a voltage here. And then you have some kind of comparator or other device with hysteresis. Here it's drawn as a Schmidt trigger gate with this little hysteresis thing in here. And this gives you clean switching between on and off. And here this one is shown as driving an open collector output transistor stage. So in the usual way with these things, you put a pull-up resistor here, and then the voltage at this node will alternate between ground and the power supply, depending on whether this transistor is switched on or off by the Schmidt trigger output here. And so all of the processing of the analog signal from the detector is managed for you. And that's nice, but I think that it's probably not suitable for our situation, because I believe it relies on having a good difference between the unoccluded and the occluded state of your optical beam. You need to go between completely unoccluded and completely occluded. And we're not quite going to be doing that because of the constraints on manufacturing this encoder disk that I mentioned last time. We're going to be going between completely occluded and partially unoccluded, which means that we'll need to be careful about setting the threshold for the comparison that goes on here. So I think we're going to be using a phototransistor kind of photointerrupter and developing the circuitry that goes on this output ourselves. So to select a photointerrupter, I made a big old spreadsheet with a few different things in it. I looked at datasheets and mechanical drawings for a range of photointerrupters, and I assessed them based on 3 mechanical constraints that I developed from the CAD modeling, the mechanical CAD modeling that I've been doing. So the first of these constraints is based on the need to align the optical axis of the photointerrupter with the holes in the encoder disk. And if we look at the the CAD model, what we're talking about here is this alignment between the red optical beam of the photointerrupter and these holes in the encoder disk. So obviously there's stuff here about the distance from the top chassis plate to the motor axis and how high the PCB is off the chassis plate and things like that. And to work out exactly how this constraint was going to work, you look at the thickness of the chassis plate, the separation between the chassis plate, and the radius of the circle of centers on the encoder disk. So if we go back to the mechanical drawing, we have the thickness of the chassis plate, so the thickness of this thing. We have the distance between the chassis plates, which is from here to the bottom side of here. And so if we start at the top of the chassis plate, we go down through the chassis plate, and then we go halfway to the bottom chassis plate, we'll get to the motor axis, the center of the motor axis. If we then go back up by the radius of this line of centers of the holes that are in the encoder disk, we'll end up with a measure of the distance between the top chassis plate and the center of the top dead center hole on the encoder disk. And if you do that calculation, you get 2.75 millimeters. So this is the distance from the top of the top chassis plate to the center of the holes in the encoder disk, basically. And so you want to make it so that the optical axis of your photoencoder, your photointerrupter, lies along that distance from the chassis plate. The second constraint is to do with making sure that your encoder disk will not bottom out in the slot. So this is just based on measuring the distance from the center of the holes in the encoder disk to the edge of the encoder disk, and then adding a bit of leeway and saying that the slot in the photointerrupter has to be at least this deep. And so what I've been doing is I've labeled these constraints C1, C2, and C3, and there are, for each photoencoder, there are cells in the spreadsheet that have Boolean expressions that represent these things, and then there's a logical and so this column that says OK, if there's an OK in this column, it means the photoencoder meets all of these mechanical constraints. The final kind of mechanical constraint is to do with making sure that there is no interference between the photointerrupter body and the body of the motor. And so the easiest way to do this is to think about the length of the motor shaft, which is 9 millimeters, the fact that you want to leave a bit of space at the end of the motor shaft, and the thickness of the encoder disk. And what that means is that you're left with this amount of usable shaft length for space. I'll show you what that looks like. So here we've got the motor shaft, which is 9 millimeters long. The distance from here to here is 2 millimeters. We leave a bit of clearance, so there's space to put a blob of epoxy or something to stick the motor encoder disk in place. The encoder disk is about 1 millimeter in thickness, and then you're left with the distance from here to here, which is 6 millimeters. And so what this constraint basically is just to say that half of the length of the photoencoder, the photointerrupter, has to fit in this gap to guarantee that there's no mechanical interference between the body of the photoencoder and the body of the motor. And you can see the way things are set up here, there's no problem with this. So I worked these things out, and then I collected all this information for a whole bunch of photointerrupters, and there are 4 companies that make most of them, it seems. There's Omron, Lighton, Rome Semiconductor, and Vishay. And I could reject a bunch of them immediately because they didn't fit some of these mechanical constraints. So there was either the slot wasn't deep enough, they were too wide, so there'd be interference with the motor body, or potentially interference with the motor body, or something else. that left me with a bunch of these things. A few of them were very marginal on this non-interference with the motor body condition. The minimum value allowed for these was 12 millimeters. And you see 11.8, 11.9 is only going to get a tiny amount of clearance. And I wanted to be a bit more sure about it, so I just rejected these. There was one funny one from Vishay that didn't have information about the optical aperture, which I wanted. So what I did with these, I looked at the mechanical drawings and I collected a bunch of parameters about each of them. The basic physical dimensions, length, width, height of the thing, information about the slot, information about the depth of the optical axis from the top of the photointerrupter, which is important for working out the centering of the optical axis on the holes of the encoder disk, and then information about the optical aperture of the photointerrupter. And so I was left with like 9 or so, and I ended up picking this one from Vishay, TCST 1230, for a few different reasons. It's a sensible size. The width of the slot is a little bit less than 3 millimeters, so there's a bit of leeway for lining up the encoder disk. The electrical characteristics are normal for these things. So ID is the dark current, which is the leakage current from the phototransistor when there's no radiation falling on it. And they're all in the 100 or a few hundred nanoamp range here. The light current for these things, so IL is the minimum light current quoted on the datasheet. They're all in a similar range, about half a milliamp, 0.2 milliamps. This one from Lighton, I don't really believe this. I think they quoted a typical value in the datasheet rather than the minimum value. This device from Vishay has a typical light current quoted of 2 milliamps, but according to the datasheet, the light current can range from 0.5 up to 14 milliamps. So one of the issues with designing the circuitry for this thing is to deal with that range, and also to deal with the fact that although this dark current is quoted as being 100 nanoamps, that's not the current you will get from the phototransistor when the optical axis is completely occluded, because there will be some ambient light in the wavelength range that the phototransistor detects, and so you will get a greater dark current than what's quoted. So we have to think about that. The other reason I picked this one is that the aperture, so the optical aperture is 0.5 millimeters wide by 2 millimeters high, and that matches up to some simulations that I've been doing that I'll talk about next time. So this seemed like a good choice to me. Now, there's another thing to look at here, though, which is that in order to get this alignment between the optical axis of the photointerrupter and the holes in the photoencoder disk, the PCB needs to be offset from the top chassis plate a bit. And so I did a calculation to work out what the required standoff distance for each of these things were. And for this Vishay device, it's 0.95 millimeters. Now, you can't really buy an off-the-shelf standoff that's 0.95 millimeters. You can make one if you really wanted to. But an N2.5 washer is half a millimeter thick. So what you can do is you can stack up a couple of washers here to stand the PCB off from the chassis plate, and that gives you pretty good alignment between the optical axis and the motor encoder holes. So I'm pretty sure this is what I'm going to do, at least for this motor prototype PCB. Whether I do exactly this for the final robot, everything all in one go PCB, I don't know, but it'll do for experimentation with this thing. So choosing this photointerrupter turned out mostly to be an exercise in mechanical calculation and constraints and modeling, which is not unexpected. The electrical characteristics turn out not to be much of an issue. They're all more or less the same, these phototransistor photointerrupters. How you deal with that, we'll talk about next time. And I've been doing some slightly amusing simulation looking at exactly what kind of patterns of currents and shapes of current pulses you should expect to get out of this phototransistor as the encoder disk spins. And those simulated current traces can then be used to drive LT-SPICE simulations, which is what we'll talk about next time. See you then.